All right, we're back recording. Got a ball launched from the ground with initial velocity 8 meters per second at 60 degrees above the horizontal. What's the approximate maximum height above the ground reached by the ball? Now, for something like this, I would want to draw a picture. Right, so see, this image comes to mind. I mean, this is what's going on, right? Like, so we got something. They said 60 degrees, so it's actually probably more like this, isn't it? A pretty steep angle. Okay. All right. And then, guys, which component is going to allow you to answer this question? How fast it's going across the field or how fast it's going strictly up? Yeah, yeah, you care all about this right here. In fact, if you were to throw a ball straight up at so that the speed matched this component, then wouldn't it just turn into this and it would be the exact same thing? Exact same thing? Okay. So that's what we're gonna do. All right, let's see. What were the numbers? It was uh 8 meters per second, 60 degrees above the horizontal. All right, so let's do that. Let's go. All right. All right, you guys are writing some your notes. We got 8 meters per second at 60 degrees above the horizontal. All right, so you got that. All right, so yeah, let's break this into components. Say, well, it's kind of going across the field, but it's kind of going up, right? And I definitely care about this component right here. Okay, hey guys, this is equal. I'll call this v initial in the y direction. Okay, v initial in the y direction is equal to what times what? 8 meters per second times sine of 60 degrees. Yeah, sine of 60 degrees, right? That's this right here, v boss sine 60. Okay? And remember, this is only initially because as soon as this uh, object is released, gravity's immediately going to start pulling it down. It's going to start slowing down. Okay, but we'll worry about that later. Okay, okay. Guys, make sure your calculators are in degrees. I had you guys, I think, switch to radians a few weeks ago and just never came up again. So hit DRG and switch back to degrees if it's not already in degrees. Okay, so is everybody's calculator in degrees now? Because it's radians. It's some weird answer makes no sense. So 8 sine 60. Okay. Sine 60, by the way, 60 degrees is the same thing as 3/2. Sometimes that's helpful to know. But let's just get a decimal value. So I'm looking at 6.928 meters per second. Okay. Okay. So guys, if you threw a ball straight up at that speed, then whatever height it reaches is the same maximum height as this ball is going to reach right here. Okay, and what is this H max? Okay, H max. All right, guys, good so far? All right, so now we got some options. We could go kinematic with that third kinematic formula, or we could go conservation of energy. So it doesn't really matter. Maybe I'll pick kinematic. Let's go with that. Okay. So let's go final velocity squared equals initial velocity squared plus 2ax. Okay. Yeah, that's just straight off this page, right? Just copy pasted this right here. All right, so same thing. And then, right. Yeah, I'm just considering the vertical motion. So let's go shape it down. Guys, at this maximum height point, what is the velocity? Zero. Zero. If you want to put subscript y, because we're just focused on the vertical. Yeah, this goes to 0 meters per second. Zero squared is still zero, whatever. Okay. Now what number goes right here?
6.9.
Yeah, this right here that we found from trigonometry. Let's go 6.928. That's meters per second. Okay, now that's got to be squared. Don't forget that. Using this method. Okay. Okay, plus 2 times. Ooh, what should I plug in for acceleration? You guys like 9.8? Okay. Do I want to do positive or negative? Yeah, let's definitely go negative. 9.8 meters per second squared. Oh, okay. Because here, you're throwing something up. If you guys know gravity's pulling down. Okay, so keep that in mind. Different directions. Okay. And ooh, what does this x represent? H max. Yeah, because that corresponds to 0 speed at the top, doesn't it? Okay, you guys see this all come together? Okay. So or if I list this in terms of variables, you get some term. Right. Anyway, so H max looks like it's going to be V naught y squared on 2g is what it is, which is 6.928 squared on 2 times 9.8. This would be meters. When you pull the units out, let's see what that is. 6.928 928 squared over, and then in parentheses 2 times 98. Okay. It's good to get calculator practice too. Like a lot of students forget to say like put this in parentheses, and then they get some nonsensical answer. I'm getting about 2.45 meters. Are you guys getting something like that? About 2.45 meters? Oh, yeah. Okay. All right. So let's look for, and you guys know AP likes to round. So let's look for the closest answer to that. About 2.45 meters here. Whoa. Well, I see a 2.4. That's probably it. Yeah. Okay. So when I click it and the box turns green, that means it's the right answer. Yeah. Okay. So you guys good with that? Yeah. All right. Number 2. A horizontal disc rotates at a constant angular speed. Oh, there you go. As viewed from above, a coin with mass m on the disc moves counterclockwise in a circle radius r. Okay. Which of the following vectors best represents the direction of the frictional force exerted on the coin by the disc in the position shown? Ooh. Okay. Well, is it if there was no force between if there was no friction force, wouldn't the coin just be hovering there? It wouldn't be moving at all, right? So what force is keeping it? Oh, okay, but the frictional force is acting as a what kind of force? Starts with a C. Centripetal, and the word centripetal literally means it's pointing towards the what? Towards the center. So what should you pick? Yeah, you guys like this A right here, like that A. Right. And then
I'm gonna say that you can say the opposite.
What's the other one? Right. Right. Here's a
I also
flip the screen here. Here we go. Here's a full free body diagram on the coin. So I'm just specifically focused on the coin. Okay, it's weight down, normal force up. Okay, and it's this frictional force, right, pointing towards it, which is acting as the centrifugal force and the net force. You can say all that. I'll let you. Okay. Here. You guys see there's enough information lying around? Actually, what this is here, you can determine what's the minimum necessary coefficient of static friction with this. Okay. This is a review lab I have lined up for you guys. So sometime in the next few weeks, I'm gonna give you guys these turntables and like little maths like this. Okay. So be thinking about this. How do you guys do a whole write-up and everything? How do you determine the coefficient of static friction? I think that might be the next question. I think, or something related. Which of the following expressions correctly represents, minimum coefficient. Oh, okay, that was it. Minimum necessary coefficient of static friction. So let's go through this piece by piece. The piece. Okay. Right. So first line. This friction force is acting as a what kind of force again? Centripetal. Okay. So that's gonna be the first domino. Right? Now we're gonna do some substitutions here. Hey guys, friction force could be what times what? We're trying to get coefficient of friction, right?
Yeah.
So how do you bring that in here?
Isn't
Yeah, coefficient of friction times normal force. There you go. Okay, something like that. Okay. Okay, and then now if I have some omega going on here, I'm thinking in terms of angular velocity. Because what's centripetal force in terms of angular velocity? Because I remember for linear velocity, but linear tangential, like mv squared divided by r, but that's not what I want here. M omega squared times r. Remember that? Okay. So mv squared divided by r or m omega squared times r. Is that really the same thing? Yeah. I don't have an O'Neill cylinder out ready to go, I don't think, but you guys remember O'Neill cylinder? Okay. In space spinning. Okay. Okay. Now I have an inequality here because we got static friction. But if you set equal, you can get the minimum necessary value. Okay. All right. So what do I want to substitute next with this normal force right here? Yeah, this has to be equal to this, right? So normal force benefit mg. So that could go like that, right? Okay. Now what cancels out on both sides? Yeah, that mass right there. Right. So it turns out if you have this here, you have this here, right? Well, if they were the same materials, then you would get the same result. Right. So the material matters, but not necessarily the quantity of mass. Right. Right. So here this up. Okay. Can you guys solve the coefficient of static friction? Divide down the g. Right. Say too, if you guys are taking notes and writing this in your notebook, then your brain is learning it that much better. Okay. So I'm looking at omega squared r divided by g. Okay. Are you guys okay with the whole process? Okay. And of course, even better if you're taking notes, you should be taking notes, helps your brain learn. Okay. So omega squared r over g. All right. Let's see if that's what we're looking for. Here's omega squared r over g. That looks like option A. Think it's A? Yeah, it's A. There you go. Non-uniform cylinder the container is filled with water. Oh, filled with water. It's probably a pressure question that we just finished covering. At which of the labeled points is the pressure the greatest? Pressure the greatest. Well, what's the rule here? Is the rule just the deeper you go, the more the pressure? Rho GH. Okay. Guys, does it matter the diameter of the container? No. Right. All that matters is how deep you are, gravity field, and the density of water. Okay. But the rho and the g aren't changing. So just whichever point's the deepest. So do you guys think point D is the deepest? So that's got to be the answer. Point D. Yeah. That's all. Just point D. A disc. Let's zoom in a little bit here. Rolls without slipping.
Axle force?
Down an incline. A force diagram, which represents the force exerted on the disc, is shown in figure 2. All right. At the instance shown in figure 1, point P, which is on the edge of the disc, is in contact with the incline. Okay. Which of the following forces exerted on the disc exert torques about point P at the instant shown in figure 1, about point P? Okay. Now, actually, this one tripped me up a little bit at first because, guys, to induce a torque to get this thing actually rolling and accelerating rolling, right? Really, you need more than one force. Guys, which two forces are actually causing it to rotate? Yeah, friction and its weight, the force due to gravity and the friction, right? But the key here to get this exactly correct, right, is to say this right here. You guys see it says about point P, right? Now, at the point P, right? And if you thought about this being like the door hinge of a door and you press really hard on the door hinges, does that ever open the door? No. So does this friction force cause any torque about the point that it's acting on? No. But which force does still cause a torque? Yeah, the weight right here. Because there's a small like door width right here. So I think the answer has to be A. Yeah, it's the force of gravity only because they said about point P. Okay? Right, because they said about point P. All right. Sphere attached to the end of a string. The other end of the string is fixed. Sphere is pulled to the left and released. Sphere swings through point Q. Oh, okay, where it's vertical. Okay. Which of the following free body diagrams correctly models the forces exerted on the sphere at point Q? All right, so that's ready to two. Let's see. I forgot to show you guys this one, but there you go. This is just the same picture they had before. Okay. All right, here we go. Here's classic pendulum. Okay, so it's pendulum swinging out forward. Okay. Guys, suppose this weight was hanging here at rest and it was not swinging. Guys, if it's not swinging, does it have a weight down and a tension up? Okay. In fact, would they have to be the same magnitude? The weight down and the tension up have to be the same magnitude? Yeah, if it's not moving. Right. But here. Maybe you can imagine if there's a spring scale, right, and I'm hanging a weight from it. Okay, and the spring scale is reading something, right? You guys can imagine that. Okay? But now if it's swinging, now if it's swinging back and forth, right, do you think the tension is going to be more than the weight? More than the weight, right? So for a string situation, the tension always follows the same direction as the string itself. Right? You have to be careful because if it's like a rigid bar or something like that, that's not necessarily the case. But for a string, like a floppity string, that's always the case. The tension has to follow the direction of the string. Okay? And the weight's always pointed straight down. Okay? Now they're looking at specifically the case where it's going through point Q, which we were right there. And that's it. You got the weight down, you got tension up, and the tension up is more than the weight down. Okay. So there is a net force. And that net force is also called the wet force, starts with a C. Centripetal. And if you wanted to, could you set that equal to mv squared over r in soccer stuff? We could solve for tension if you know how fast it's swinging or something like that. Right? The faster it swings, the more the tension is going to be. Okay? Right. Guys, are you ever look at option A? Are you ever going to label a force centripetal force? Are you ever going to label that on your free body diagram? No. Right. So always just the classic forces maybe could conspire and act as a centripetal. Right. Do you guys like option B? Yeah, I think I like that one. Yeah, that's gonna be it. Okay, so weight down, tension up, mismatch sizes. Right. All right. Yeah. So don't label centripetal. Right. Guys, what's wrong with option D? Yeah, same magnitude, which would only work if it was hanging at rest, but it's not hanging at rest, so it can't be D. At 7, at time 0 seconds, an object is moving with a velocity that can be modeled by this equation. Okay. Guys, does this look like V equals V naught plus AT, the second kinematic equation? When does the object change its direction of motion? Right. Well, in a physics context, if something's changing its direction of motion, what variable is equal to what? Velocity is equal to zero, zero. Yeah, zero velocity. Okay. Guys, so if something's turning around, it has zero velocity at the point. Because if you throw a ball straight up and you want to find its maximum height, isn't one way to think about that? Well, I know that at its maximum height, it would have zero instantaneous velocity. That'd be true, right? Okay. So let's set that. Here, I'm gonna write that equation down over here. Write that down. Right. And of course, you guys are writing that in your notes also. I got V equals 4.2 meters per second minus 1.4 meter per second squared T. Okay. And flip the screen over. Point. Okay. So here, just to point this out, you guys do see it? This right here is the second kinematic formula. It's the same thing. Okay, same thing. So this is this. Okay, and we're gonna set this equal to 0 meters per second, and soon we'd be turning around. We're gonna solve for how much time it takes. Okay, so I'll subtract 4.2. That's negative 4.2 meter per second equals negative 1.4 meter per second squared T. Okay, notice how I'm keeping my units attached. I almost always do. Because when you divide this over, you get T equals negative 4.2 meter per second over negative 1.4 meter per second squared. Okay, all the units cancel except for what? Yeah, one of the seconds, and that comes back up on top, and that can describe time. All right, so what is 42 or 14? I'm looking at, oh, that's a 3.0, and that'd be seconds. So it looks like at the 3-second mark, it's turning around. You guys think? Okay. You guys like 3 seconds? Let's check this out. Is there a 3-second option? Looks like B. It is B. Oh yeah. Oh yeah. All right, number 8. Graphs show the magnitude of force exerted as a function of position. Right. So I bet when I scroll down here, we're gonna see F versus X. Guys, already, just if you stop right there, what's probably the question that's going to be asked? If you have a F versus X graph, what's the most opportune question? Work. And work is what property of the graph? Area under the curve? Ooh, I hope I'm not misleading you guys. Okay, 2 trials, force exerted, both trials. Oh, W1, W2 are the work done. Yep, there it is. All right. Object moves from 0 to 1 meter. Okay. And so I know the graphs are really tiny, but they could both be F versus X. Is that okay? Okay. How do work 1 and work 2 compare and why? Ooh. Right. So now, you guys just told me. How? You guys just told me. If you have a force versus distance graph, the area under the curve represents the work. Now I just have a constant force here. They have a variable force, but it's the same principle. It's still the area under the curve. Okay? So really, that's what we're comparing, isn't it? Is which one has more area under the curve? You guys, which one has more area under the curve? Yeah, it's got to be a scenario 2, doesn't it? Okay, because you made a straight line shot. This one's shaving off a little bit. Straight line shot. This one's adding a little bit. Yeah, this one has to have more. So I think work 2 is more than work 1 because there's more area under the curve. So let's see if we look at, okay, work 2 greater than work 1 because the area under the curve of force 1 is smaller than that of force. I think that's the answer, isn't it? Is it A? It looks like A. I think it's A. Yeah. Okay. All right. All right. Now, yeah. Okay. It's okay. Number 9. Projectile launched initial speed v naught angle theta naught over the horizontal, the projectile follows this trajectory. Okay. Okay, it's all there. Which of the following pairs of graphs best represents the vertical component of velocity? Oh, and acceleration, as the projectile is functions of time. Okay, let's come up with those from scratch, and then we'll figure out. Also, here, but before I flip the screen, do you guys notice going to the right is the forward direction? That makes sense horizontally. Okay. Now, vertically, guys, what are they defining as positive in the vertical direction? Up or down? Up. Do you guys see up as positive? Okay. Now, a lot of times back in the notes way back in the day, like if we were at the edge of a cliff and you dropped a ball, I told you to define down as positive. Right. So a lot of the graphs they give you are probably upside down of what we're doing right here. Okay, so be ready to feel that both ways. Okay. Okay. So here's what I'm talking about. If you go to the edge of a cliff, and you throw a ball upward, okay. Say I have the ball like moving up and then down. Okay. Like if you turn this graph upside down, it actually looks a lot like what's actually going on. Okay, is that? Okay. Right. And then in terms of velocity versus time, again, if down is positive and you're throwing it upward, you're throwing it in the negative direction. Okay, so velocity versus time goes like that. Okay. And acceleration, well, if gravity is always pulling down, then it's constant positive acceleration. Okay. Right. But so to answer the question that we're trying to answer on AP, okay, so here's the actual ball in motion. All right, watch this thing go across, something like that. Okay. They're saying let's call up positive and right positive. Okay, so let's do velocity versus time and acceleration versus time. So velocity in the y direction versus time, and acceleration in the y direction versus time. Okay, maybe we should make these like sideways t graphs. Okay. All right. So again, up is positive. Okay. So guys, initially, is it moving in the positive or negative direction? Positive. Yeah, positive. How we're framing it this time. Okay. And what's the vertical component of velocity right here? 0. And after that, moves which way? Negative. In fact, faster, faster, faster. Okay. You guys, velocity versus time. What basic shape should this be? This is a parabola, straight line. What is this? Straight line. Yeah, straight line. So it should go basically like that. Okay. Okay. Now acceleration in the vertical versus time. Okay. We're talking about gravity, right? Is what? Yeah, constant negative. Okay. In fact, I think you guys know a value right here. What's this value right here? Yeah, negative 9.8 meters per second squared. Ooh, what's the slope right here? Negative 9.8 meters per second squared. Yeah, let's see if we see something like that. I think it's what they're looking for. Yeah. Okay. Okay, so now the acceleration's not changing. Oh, is that what we drew? B? I think that's it. Yeah, that's it. It's B. Okay. Four constant forces are exerted on an object. Okay, mass 2 kilograms. The figure represents the forces of the objects. Okay. Okay, now this one you got to zoom out so you can see all the forces. And so I'm gonna draw that picture before I flip my screen, and you guys can draw that in your notes also. So I'm drawing that picture. You guys are drawing that picture. We're all drawing that picture. Right, so I got the mass right in the middle. Okay, got 17 newtons up. Got 20 newtons down. Got 3 newtons left. Okay. And then let's see, 5 newtons up and to the right at a 37-degree angle from the horizontal. 5 newtons. Yeah. Okay, 37 degrees. Okay. Hey, you guys got that picture? All right. So premise here. And the mass here is 2 kilograms. Okay, so we'll come back to that later. Okay, what was the question? What's the what's the object? Oh, how long will it take to pick up to a certain speed? Okay, guys, there's going to be a lot of little parts to this. Okay, so we're not going to address this question right away. Okay, but first let's get the net force, and then we'll see where this goes.
Well,
All right, so you guys got the same picture here?
1 unit to the
All
right.
right, let's start with this 5 Newton force at this 37-degree angle. Let's break this into components. Guys, what's this component here?
Second.
Yeah, equals 4 newtons. And what's this component right here?
3.
Yeah, equals 3 newtons. Okay, so it effectively replaced the 5 newtons in terms of its components that are now aligned to this Cartesian system. Okay?
It's not.
And you guys knew it's a 3, 4, 5 triangle from 37 degrees. Okay. If it was any other angle, could you go to like 5 and then sine of that angle? That's how we're getting this. And then if I flip it to cosine, that's how we're getting this. Okay, so that's where that comes from. Okay. So now, what's the sum of the forces in the y direction? 0. It is 0 because it's 17 plus 3 minus 20 equals 0. Okay, so there's no force in the y direction. What's the sum of the forces in the x direction? Huh? 1. 1 newton, right? Because I got 4 newtons going to the right. I got 3 newtons going to the left. So subtract them. Okay. I'm getting 1 newton. Okay. Okay. Now, if there had been forces in both components, could you add them back together, maybe with Pythagorean theorem to get magnitude and maybe an inverse tan to get the angle if you needed something like that? Okay. Yeah, you could. Okay. But you can see here that the overall net force is just what? Yeah, 1 newton. Right. So we have net force equals 1 newton. Okay. And we have the mass at 2 kilograms. Ooh, what law of motion am I about to bring up next? Huh? Yeah, F equals ma. Okay. So acceleration is net force on mass. That's Newton's second law, isn't it? Newton's second law. Okay. So we got a 1 Newton force acting on 2 kilograms. So it's going to be accelerating at 1/2 of a meter per second squared. Okay. Now that's the acceleration. All right, guys, good so far? Okay, gotta go back to the question. Okay. So we know the acceleration at this point. Is that how much time does it take to get to a speed of 2 meters per second? Did it say start? It probably starts at rest, right? Probably does. Oh, wait, there it is. Yeah, thanks. Okay, okay. We gotta get up to a speed of 2 meters per second. Does this sound like a job for kinematic? No. I think. Okay, let's do a little tax PV table. All right, starts from rest. We got to get to 2 meters per second, and we're accelerating at 1/2 of a meter per second squared. All right, so we got all those values. Okay. And the question is how much time? How much time does that take? So which formula? Which kinematic? Yeah. You guys like the second one? The second one is the only one that does not have the x in it. Right? These other guys have the x. This one does not. Okay, and they never asked us anything about or told us anything about how far. Yeah, let's go. V final equals V initial plus AT. Okay, look up. All right, so we're going to 2 meter per second from 0 meter per second. We're picking it up at 1/2 of a meter per second squared for some time. All right, so how much time did that take? 4 seconds. I think that should be the answer. Look about right. All right, guys, got that? Everybody got that in their notes? Got it in your notes. Okay, so here's a poster version of rundown of what we did. Okay, so if we had to break this into components, yeah, I like 37-degree angles because that sets up 3, 4, 5 geometry, so that's nice. But more generally, you can use sine and cosine. Okay. We had to add the vector components and vectors together. Okay, so think about like that. We had to kick over to Newton's second law of motion. So once we got the net force, we had to kick over to Newton's second law of motion right here. Second law. Right, and figure out what is the acceleration. And finally, once we had acceleration, we could go to those kinematic formulas and do some kinematic. Okay. And we got, okay, and then that finished out like this right here. Okay. That's all kinematic right there. All right, we got 4 seconds it took. All right, let's see if there's a 4-second option. It looks like D. It is D. Oh yeah. All right, you guys good so far. Good so far. All right, 11. At the instant shown, three identical asteroids are in a line. Okay, yes, when they say identical, most importantly, they have the same what? Mass. Yeah, definitely mass. Yeah, that's what's gonna matter in physics. Okay, equidistant. Okay, so this D, same. The asteroids are in empty space, right? So you can consider a closed system. Right? The only forces on each asteroid are from the other asteroids. The positive x direction is defined to be to the right. Okay, so it's also shown up in the figure. Okay. Which of the following correctly ranks the magnitudes of the net forces exerted on asteroid A and asteroid B? Right, so FA net and FB net. Right? Well, guys, let's start with asteroid B. Asteroid B right here. Has asteroid B been pulled to the left as much as it's being pulled to the right? So what is the net force on asteroid B? Zero. Yeah, there's zero net force. It's not going to accelerate at all. Right? May as well just be sitting there. Right? Now, what about asteroid A? Is asteroid A being pulled to the right due to B and also due to C? Right? If all we're doing is just ranking the magnitudes, then isn't any force greater than zero? Of course. Right? So I think FA has to be greater than FB. Notice it says net. Right? Okay, FA net greater than FB net. Okay, this is a good start. The net force on oh, is it okay? That's also true. That's probably the answer right there. Let me make sure it's not D though. Okay, which starts out okay. The force on asteroid A exerted. Okay, that's definitely wrong on D. Right, opposite direction. It's got to be C. It is C. It is C. All right, you guys give us C. Give us C. Okay, and then if you had to do a larger calculation, you guys know it could link back to this. Somebody with this, right? Okay. All right, so there's this inverse square relationship between the force and the distance. Okay, so all that's going on. If that mattered, you had to do that calculation. All right, number 12. Got an object traveling across a flat horizontal surface with constant velocity, v, when a net force of magnitude F is suddenly exerted on the object. Okay. Which of the following cases does the kinetic energy of the object remain constant? Kinetic energy. Well, you guys know kinetic energy, 1/2 mv squared. You guys know that. Okay. So but I don't think the mass is going to be changing. So really, you don't want the speed to be changing, right? As long as the speed doesn't change. Right. Now, this one, let me see show of hands. What do you guys think? I'm going to scroll down to their choices here. All right. So option A, the force is exerted at less than 90 degrees from the direction of velocity. Here, I'll read them all first. Okay. Option B, the force exerted in the same direction as the velocity. C, the force exerted in the opposite direction of velocity. Or D, the force exerted at 90 degrees to the velocity. Okay, so go back to the beginning. Let's see, show of hands here. Show of hands. How many of you guys thought the answer was going to be A? Who says A? Does anybody say A? I would have picked A. I would have picked A. Okay. Option B, who says the same direction as the velocity? C, who says the opposite? And who says D at 90 degrees? Who says D? Okay, yeah. Now, if you're picking that one, AP also shows that. They're saying the answer is 90 degrees. I don't think that's correct, though. Right. So, and I'll try to you guys why. Okay. So, right, we got this object. Okay, it's in motion. Let's say it's like going to the right. Right. Okay. Well, now if you push to that direction, it's going to speed up. That would be increasing the V and therefore increasing the kinetic energy. So that's no good. Also, if you push it the opposite way, slow down, that would also be changing the D. Okay. Now, what they're claiming is if you put a force that's at 90 degrees, okay, because if you do that, aren't you speeding it up in perpendicular? Okay. And that kind of reminds me of that plane question from a long time ago. I was going to a crosswind. Okay. Wouldn't that necessarily have to make it speed up overall? Because it's not speeding up or slowing down in the lateral direction, but it is speeding up perpendicular. So overall, it would have to speed up, wouldn't it? Right. Huh?
Round. Push down. Can't really go.
But that wouldn't be a net force because then the ground would be pushing back. Right, something like that. So you're talking about a net force. Right. Now, if you instead pushed in like this direction, it would be speeding up due to like Pythagorean components like this, right? But it'll also be slowing down a little bit laterally, and those two effects could cancel it out if you got it at just the right force at just the right angle. Okay? That's why I would pick A. AP saying the answer is D. So I don't know. I think they missed that one, but there it is. All right. 13. A block is pushed up an incline with a rough surface at constant speed. Ooh, rough surface constant speed with a constant force F, which is parallel to the incline, as shown in the figure. All right. Okay, so we're pushing this block up and it's going at constant speed. There is a coefficient of kinetic friction, mu k. When the constant force F moves the block up the incline at speed v. Oh, the power. Ooh, we got a power question delivered to the block as P1. When the block is moved the incline with speed 2v, it's double the speed. The power is defined as P2. What's the ratio P1 to P2? Right, now this one involves a little bit of a deep cut trick here. Here, so power is rate of work, rate of energy transfer. That could be work over time. So you guys know that. Yeah, you can rearrange it. A lot of times there's an elevator scenario. That's why I drew an elevator here. Right? Could you guys say power is force times velocity? Do like that? Here. Okay, so this breaks into that, leads to that. Okay. Now, maybe you're pushing with this. I think it would have to be the same force either way, wouldn't it? Because constant velocity, right? There's some friction that doesn't change. The weight of the block and sine component of the weight that doesn't change. So I think your pushing force would have to be the same as long as to maintain constant velocity, regardless of what that velocity is. Okay. What is definitely changing is the speed is becoming 2v. So we're doubling the speed. But guys, if we're leaving the force the same, but we're doubling the speed as a result, or doubling the speed, what happens to the power? It also gets doubled. You guys see that? And so you have to know that, what you're looking at right there, to be able to answer this quickly. Right? You get about 2 minutes per question. You'd find out, right? And so I think P1 to, okay, and then they, how do they order this? They ordered it P1 to P2. So really that should be a what to what ratio. Yeah, 1 to 2. I'm looking for 1 to 2. Because, okay, sometimes they'll have, I think A would probably throw off a lot of people. Yeah, it should be 1 to 2. There it is. 1 to 2. Okay. Okay, so I think it's the same scenario, isn't it? Same scenario. Which of the following correctly describes the work done by gravitational force and the work done by the normal force as the block moves up the incline? Let's start with the normal force. Guys, normal force. Normal force is pushing perpendicular to the plane, and the direction of motion is parallel to the plane. So by definition, in that scenario, how much work does the normal force ever do? 0. Yeah, 0 work. Okay? So normal force is normal force definitely does 0 work. Right? So that one's 0. Okay? Now for gravity, do you think it has something to do with like mgh? No, because gravity's pulling down with mg, but the block is actually moving up some distance h. Okay? And because whenever those directions are opposite, the force is pulling down, but overall the block moves up. Is that considered positive or negative work? Yeah, that would be considered negative work, wouldn't it? Negative work. And I'm thinking maybe some kind of like this in the back of my mind too. Right? So something to do with force times distance. Right? Force times distance. Right? For work. Right. What options do we have here? Oh, okay. So normal force has to be causes 0 work. Right. So that narrows it down to either A or C. Right. And then work done by gravity would have to be negative. Okay. I think the answer has to be A. Okay. Are you guys good with A? Guys good with A? All right. Let's see. Let's see what's A here. Yeah. All right. 15. Students have a solid disk, circular ring, and a square loop with masses and dimensions shown. Okay, I think they're all equal mass and comparable radius size. This is going to be a rotational inertia question, probably. The dot at the center represents the axis of rotation. Which of the following? Oh, yeah, there it is. Rotational inertias. Yeah, that's what I was looking for, something like this. Okay. So, something about rotational inertia. Okay. So, I remember, like, for a point mass, it could be mr squared. If you have a bunch of points, you can add them all up, mr squared. Okay. Yeah. And then if you start to make some comparison, like, I think these two could be showing up, right?
No, it's not.
Right, no,
Acceleration.
I think all those objects had the same mass and like a comparable type radius. Right? So really, how is the mass distributed? Right? And the more closely to the center of axis of rotation, the less rotational inertia. And the more spread out it is, the more rotational inertia. Okay, like all else equal, like same mass, blah blah blah. Right. Okay. That's cool. Okay, so if we were to rank order these, I think I would say the disk has the smallest amount of rotational inertia. This ring has the middle amount. And this loop, where the quarters are pushed out even further from the center, well, that would have to have the most, wouldn't it? So I think you're looking at the rank order. It goes disk is the smallest, then ring, then loop is the most. Okay, so disk is the smallest, then the ring, and the loop is the most. That should be D. Does that look like D? Is that right?
Yeah.
Yeah, it is. It's D. It's D. All right. Two systems are in oscillation. A simple pendulum consisting of a sphere. Do we have a pic? No, no picture. Of a sphere on a long string that swings through a small angle, and a block oscillating on a spring. The block spring system takes twice as much time as the sphere string system to complete an oscillation, so double the time period. Which of the following changes could be made so the system oscillates with the same time period? All right, well, let's definitely draw this out. Block system takes twice the time. Okay. Okay, so here's your classic pendulum, and here's your block on a spring. Okay, again, really similar looking formulas, right? Really similar looking formulas. Okay, so let's get this all on a page. So we do some math here. Oh, actually, you know what? We got 1 minute to the bell, so I'm not gonna have time for this. So tomorrow we'll have to head up with the pendulum and the block on the spring.